Hello GCC Computer Studies students. Right, this is the second part of part 3 where we need to deal with some of the calculations you may be asked to do when talking about file sizes and storage. So, a couple of things to bear in mind. First of all, you're not allowed a calculator, and so in the past, where calculators were allowed, you were kind of expected to use the exact value of 1024 bytes per kilobyte and 1024 bytes per kilobytes per megabyte, and so on and so forth. In the absence of the calculator, you may assume that the value is 1000 and not 1024. Now, something else which we've not talked about yet is files, when they're stored, don't only store the data of the file. You need to allocate storage space on a disk for what is known as the overheads. Now, the overheads make up roughly about 10% of the file size. That's the general rule of thumb. And this is for metadata relating to the file, like the date, the time, how the blocks are arranged on the disk, and so on and so forth. Now, working out 10% is actually pretty easy. Let's suppose I have a value of 1234. If I divide that by 10, I simply shift my decimal point. It becomes 123.4. So 1234 plus the 10%, try it again, plus 10% would simply be 1234 plus 123.4, and when I add that together, I simply get 1357.8. So that's roughly how you do a overhead addition. So without further ado, we're going to look at some calculation examples. When dealing with databases, before we do that, it's important you understand and know how many bits and bytes, etc., are used for each type. When it comes to characters, we're going to assume 1 byte or 2 nibbles per character. In other words, we're assuming the ASCII character set. When it comes to Boolean, this will be 1 byte or 2 nibbles. And the numeric types, which are either integer or float, we will assume to be 4 bytes in length. Dates, you need to assume take up 8 bytes. So in general, char and boolean, 1 byte piece, numeric values 4 bytes, and dates will take up 8 bytes. So we're now going to look at 4 calculations. We begin with a simple text file. So the question was, I think, a text file with 1000 bytes, 1000 characters will hold how much space? Well, remember, so the calculation rule is simply this: 1 byte per character plus 10% for overhead. That's the rule that we're going to be using. So that's my formula, if you like. So 1000 byte file, 10% of that will be 100. So timesing about 1.1 or adding 10% onto the 1000 will give me 1100 bytes. So they want to know how many bytes this is in kilobytes. I simply take my 1100 divided by 1000, and that then gives me that's should be 1.1 kilobytes. Don't know what happened there. It should be 1.1 kilobytes approximately. Databases. So a database, for example, has 4 fields: first name, which takes up to 10 characters, a surname, which takes up to 10 characters, a date of birth, and the number of children, which clearly must be an integer. So the first step is to work out how many bytes each record occupies. Well, in a string, which is the same as text, each character is a single byte. So a 10 character string will take up 10 bytes, and likewise for the surname, also consume 10 bytes. date of birth being a date will take up 8 bytes. Number of children will consume 4 bytes. Adding this all together gives us a total of 32 bytes per record. I now need to multiply. The question is, the database will need to store 100 records. So I simply take the 32 multiplied by 100 and get 3,200 bytes. To this we need to add our 10% overhead. So in other words, we simply are adding 320 onto 32,000, which gives us 3,520 bytes. Dividing this by 1,000 gives me the value in kilobytes, which is 3.52 kilobytes. A third example, we look at an image. Remember, images are made up of pixels, and each pixel will represent a color. How the pixel is represented is down to the method used to represent the colors. If we're using a 24-bit encoding system, then we have 3 bytes per pixel, but sometimes we use a lot less than that. The other thing to consider is the resolution of the image. So the width by the height. So in this example, we've been told an image is 1000 by 700 pixels, and it has 256 different colors. Right, so you would need to understand that you need only 1 byte. So the color depth will be 1 byte, or 8 bits. You need only 8 bits to represent 256 colors, because there are 256 states in 8 bits. So this then means the total number of pixels we have would be 1000 by 700, which would be 7,000 pixels. We multiply the pixels by the bit depth, which is just simply multiplying by 1. So therefore, the file will take up 700,000 bytes. Adding my 10% overhead gives us 770,000 bytes. Dividing that by 1,000 gives us a value of 770 kilobytes approximately. Our final example deals with sound. Sound is stored or digitized by sampling or taking snapshots every number of over a certain time interval. The sample rate, this is called, is normally measured in hertz. So this particular sound file has a sample rate of 10 hertz. That means every 10th of a second, or 10 samples are taken every second. Furthermore, you need to know how many bytes are being used to represent the height of each of those samples, and this is called the bit depth. The calculation formula is therefore bytes per sample times the sample per second times the number of channels times the duration. So this particular sound has a file will have, well, the information we're given. A sound file has 2 bytes per sample, so in other words the bit depth is 2 bytes, 10 samples per second, and over 2 channels for 30 seconds. So bytes per sample we know is 2 times the sample rate, which is 10, times 2 channels times 30 seconds gives us a total of 1200 bytes. Dividing that by 1000 gives us 1.2 kilobytes. Adding 0.1k as our overhead onto it gives us a final value of 1.32 kilobytes approximately for this sound file. And this concludes the section 1.3 on storage. Thanks for watching, happy studying and practicing. Mr. Holmes signing off.